Hello, everyone. Welcome back from what's hopefully been a nice break over Christmas and New Year's. Today we have Sejr Pedersen, who is going to be talking about splitting Madsen-Tillmann spectra.
Yeah, thank you, Yulia, for the introduction and for the invitation to speak. As mentioned, this is about splitting Madsen-Tillmann spectra, and the rough outline is I'm going to introduce some of the basic history that led to the definition of these spectra and why we're interested in them. And then I'm going to tell you a little bit about what our contribution to the story is. And I should mention everything here is joint work with Andy Senger. Or, I mean, at least all our contributions are joint. Okay, so let me start with sort of the history for the people who are not familiar with this part of the story. So this is about moduli spaces of manifolds. So let's just fix a closed-oriented N manifold M, and we consider the space of embeddings, smooth embeddings, everything should be smooth, of M into R infinity. And here the orientation preserving diffeomorphisms act on this space by essentially precomposition. And with some not super trivial analysis, you can show that this gives quotienting by this action gives rise to a principal diff M bundle like so. And if you're in this business of classifying spaces, of moduli spaces, this is one way of defining the moduli space of manifolds that are diffeomorphic to M. So the point is, why do we consider this as a moduli space? Well, the points consider of manifolds sitting inside of R infinity, and they're abstractly diffeomorphic to M, but we don't remember any sort of smooth atlas or smooth parameterization data. So we're really thinking of them as just abstract subsets sitting inside of Rm or R infinity. And they're all just a copy in some sense of M. Okay, and if you're in this business of classifying spaces, then this should look familiar to you, namely, I guess as a consequence of either sometimes it's called the strong Whitney embedding theorem. This is the space of embeddings is contractible. I mean, Whitney gives that it's non-empty, I suppose. And then if you work a little more, you can in fact show that it's contractible. So this is a contractible space with a free action by diff plus M, such that the quotient is a principal diff M bundle. So this is exactly a classifying space for BDiff. So this gives us a nice geometric model for something which is on its face just a homotopy type. And this sort of geometric model is very useful for various constructions that I don't see how you can do just working with this as a homotopy type. Okay, so again, this is maybe old news to some, but why are we interested in something like this? Why is it called a classifying space? Well, one of the properties that it enjoys is the fact that homotopy classes of maps into it exactly classify smooth fiber bundles with smooth manifold fiber bundles with fiber M. So for every classifying space, I mean, this is how we were constructing it. You have a contractible space and you have a universal bundle of the type that you're classifying like this. And for every continuous map, you can form the pullback bundle. Let's just say E, like this. And the correspondence, or like the bijection that I have here on the slide, exactly tells you that up to homotopy for the map F, every bundle arises exactly in this way. So information about BDiff tells us about what bundles a space supports. And conversely, it also gives rise to invariants of this bundle or these bundles. If you compute the cohomology ring of BDiff, then you can then pull back elements there, and that gives rise to characteristic classes of bundles, just like you're used to with Stiefel-Whitney classes and Chern classes and stuff like this. So these are really very interesting and complicated objects. And yeah, lots of study has gone into them. Okay, yeah, this is what I just said. One particular case was sort of great interest, which is namely the case where M is a genus G surface, and inspired by some algebraic geometry that I don't quite understand, David Mumford was led to this conjecture, namely that the cohomology of this classifying space with rational coefficients is free polynomial up to a certain degree. Yeah, I don't know exactly where he came up with this. These kappas here are called the kappa classes of the Miller-Morita-Mumford classes. And so you're essentially saying that this has a very nice description, at least rationally. And as far as I know, even though this is a conjecture inspired by algebraic geometry, all the proofs are deeply within the realm of geometric topology. So it seems like this is somehow beyond the reach of algebraic geometry, at least currently. Okay, this was settled by Madsen and Weiss, and for their construction, for their proof, the following construction was of great importance, namely the scanning map. So this is a map from your classifying space, well, at least some sort of finite stage of it, that works as follows. Remember, we're thinking of this moduli space as manifolds sitting inside of RD. And so there are D coordinate directions, and the scanning map is sort of visually explained here by imagining that you have a extremely powerful magnifying glass and you run it along all the D coordinates of RD. And since the manifold is compact, most of the time you're not going to see anything. So you scan the empty manifold, and that's going to give the base point over here, where the loops are also based. And as you approach the manifold, you're essentially scanning the tangent planes. So every manifold has a tangent space at that point, and this is what you're recording. And then you land over in this space, which is the affine Grassmannian of n planes in RD. And as you scan all D coordinates, this gives you a map into the D-fold loop space. And this is compatible with increasing D. So if you let D go to infinity and take the colimit, what you end up with is a map from the full classifying space, or the moduli space, into now the infinite loop space of the affine Grassmannian of n planes inside R infinity in some sense. And this is a very interesting map, but a priori, it doesn't remember anything about M, right? The target you see is independent of M. So hoping that this remembers any sort of homological or homotopical information about BDiff and therefore M seems a little far-fetched. But what you can do for at least surfaces is that you can try to form stabilization maps. So even though you're interested in the closed surface with no boundary components, if you actually add a boundary component by just cutting off the disk, you have these stabilization maps that essentially takes, like here, the partial means that you're fixing neighborhood of the boundary pointwise, or like the identity on the boundary. And so if you're on the identity on the boundary, when you glue on another genus, you can just extend by the identity. So that's what we mean by this stabilization map. Right. So once you form the colimit along this system, you now have some hope of maybe recording something about M. And this gives rise to the map alpha. And now I've switched notation to one of these Madsen-Tillmann spectra. So this is the same as the affine Grassmannian, or it's the same as this guy. So this is the target of the scanning map. And what Madsen and Weiss actually proved was the following conjecture, the strong Mumford conjecture, namely that this map alpha induces an integral homology isomorphism. So somehow by making the statement stronger, it became easier to prove. Just having sort of the rational cohomology, making the target some polynomial ring, then you would have a map that's purely algebraically defined, but somehow having a space level version of what your conjecture should be allows you the flexibility of working within spaces and doing operations there that are not as intuitive or as available on the algebraic side. And I guess some of the history here is pretty interesting. So, I mean, Tillmann and Madsen already stated this conjecture, and this was based on a very interesting computation or observation by Tillmann herself, namely that if you took this BDiff of sigma infinity 1 and you just plus constructed it once, then this was in fact an infinite loop space. So somehow you knew abstractly that the target should be a homology isomorphism to an infinite loop space that you could then plus construct to get an actual equivalence. And once that was sort of in the air, this conjecture was settled within, I think, a decade or something like that. Okay, so that settles sort of the prehistory or the sort of later history. And then this was vastly generalized by Galasius and Randall Williams to the even dimensional, high dimensional manifold case. So let me just, you can make similar statements with various conditions on the fundamental group, but let me just state it for simply connected manifolds. And the case that will concern us the most is sort of this generalized genus G surface. So take the product of Sn with Sn and take the connect sum G times and then remove the interior of a 2n disk, just so that you have something to stabilize with respect to. And this is the WG1s. And then for us, the analog of this MTSO is this Madsen-Tillmann Spectra MT theta n, which is the Thom spectrum of a certain virtual bundle sitting over some connected cover of BO2n. So yeah, there are a couple of things to say about this Thom space. The virtual bundle, like this minus sign here, is going to be telling us that usually when we make Thom spaces, this has something to do with a normal bundle. The minus here essentially switches it to be tangential data. And then this connective cover is simply reflecting the fact that the manifold itself is n-connected. Okay, so this is going to be the target of a general scanning map. And this is what, well, this is one of several statements that Galasius and Randall Williams proved, namely they write down an analog of the scanning map, but now the target is the infinite delooping of this Madsen-Tillmann spectrum. And this is homologically highly connected, G-3/2 connected. So when you pass to the limit on the co-limit on the left-hand side, you get something that's an actual homology isomorphism. So when you plus construct it, you get an actual equivalence. This is how these things are proven. And for us, like the basic observation that is that this belongs to the realm of belongs to stable homotopy theory. And we will try to access this using sort of classic tools of stable homotopy theory. And of course, we are still interested in BDiff principally. And the main name of the game is that we're going to try to translate some of what we figure out homotopy theoretically on the right-hand side to information about geometry on the left-hand side. But that is still sort of not completely settled. But let me mention some applications. Of course, there are a plethora of applications of this great result. In a separate paper, they also determined essentially the abelianization the mapping class group of these surfaces. So pi1 essentially. And this was then used by Manuel Kranek and Jens Reinhold to figure out some divisibility results for signatures of manifold bundles over a surface. And you see a calculation of pi1, and you can ask, what about pi2? What about pi star for general homotopy groups? Can we calculate them? And can we use such a calculation for anything? And I guess that motivates the main result that we figured out. So let me just throw some stuff at you just so I can state the theorem somewhat precisely. So there is a exact sequence of spectra given like this. And I will say in a range throughout this talk, which means that these things don't hold exactly. But if you take some truncation, then this will, like if you truncate and throw out all the higher homotopy groups of past some point, this will in fact be an exact sequence. So the first term here is stunted projective space. These are also very classically studied, going back to, I think, atoms and this vector fields on spheres problem. And then on the right-hand side, you have a sort of more familiar object, namely just the Thom spectrum of almost the canonical bundle over BO. You just take a connective cover of it. And our main contribution is to show that in a range, this exact sequence splits. So this L here means that exactly once you truncate to degrees less than or equal to 5n minus some constants, 5n over 2 minus some constant, you can in fact split this sequence. And this 5n gets transformed into an n over 2 because everything has just been made 2n connected from the start. So once you subtract that off, you really get some interesting information. And it tells you that you can sort of access the homotopy groups of this left-hand side in this range in terms of, well, this stunted projective space and this sort of slightly more difficult object here. The stunted projective space here is sort of computationally accessible, and this MON thing will contain all the difficult information about the homotopy groups of spheres. So yeah, that is what it is. You can sort of get away with reducing stuff to saying, well, this is just as difficult as computing homotopy groups of spheres, and then you're still allowed to have a theorem. But this is just the state of the matter. Okay, so let me get into the proof. So let me start by saying why we get this exact sequence and why we only get it in a range. So if you start with this diagram where the left-hand side is a homotopy pullback square, then you can apply this wonderful fact given to you by Blakers-Massey that, well, spaces are not quite spectra. You're not a homotopy pullback if and only if you're a homotopy pushout, but this is true in a range. And here the range is 2n plus k plus 1. So this is a homotopy pushout also in the range 2n plus k plus 1. And that comes from the fact that, well, you add the connectivity of these guys. This is 2n connected and this is k connected. And then there's a plus 1 for reasons. So this is in fact also in this range a cofiber sequence. And then these are all spaces over BO. And sort of our modern understanding of the Thom spectrum functor is that this is a functor from this infinity category of spaces over BO to the infinity category of spectra. And it's essentially given by taking the co-limit over of the diagram defined by the underlying spherical fibration. So in particular, it preserves homotopy co-limits, in particular the homotopy pushout that is in a range. And it also plays nicely with connectivity. So once you apply the Thom spectrum to the diagram, you get exactly just the suspension spectrum of this guy, because yeah, the map to BO from this guy is null homotopic, so you're just taking the sum space of a trivial bundle. And then, oh yeah, I should mention, what is this -1 doing here? Really, as I mentioned, sort of when I introduced briefly this Madsen-Tillmann spectrum, this has to do with tangential structure. The map to BO is typically something having to do with the stable normal bundle. And the way to interchange them is essentially that, well, BO represents bundles on your space, and there's, if you at least look at the virtual bundles, there's a way of taking -1 and sending everything to its inverse. And this map is represented, or this operation is represented by a map from BO to BO. And you sort of twist by this, and then you pull back. That's just going to interchange everything from normal bundle to tangent bundles. So if you do this, and this is what you pull back, instead of getting MOK for the first term, you do exactly get this MG theta and for this suspension. And then you have some other space, that's the cofiber, but you know that maps highly with a highly connected map to, again, the Tom space of this connective cover of BO, which is MO as well. So that's how you get this exact sequence, in fact, for any k between 0 and n. And this will be useful for later, that we can do this not just for connectivity n, but for any connectivity between 0 and n. And then lastly, there's just a classically defined map from the standard projective space to SO mod SO2n. And this is basically 4n connected. So we're going to work in ranges that are much less than this. So this is maybe worth remarking that if I switch between those two, it's because I will treat them interchangeably. So for us, in a range, we're always going to be truncating at something that makes this highly connected map an actual equivalence. So if I switch between them without mention, and that's confusing, this is what I'm doing. Okay, so we have an exact sequence. We want to split it. What is the simplest thing you can try to do? Well, you can try to show that one of the maps in the sequence is simply null. Then by just virtue of being fiber and cofiber sequences, you can find a splitting. So for us, we'll in fact look all the way to the right and think about the connecting homomorphism and try to show that this map is null homotopic in a range. And that range will give us exactly the splitting range in the theorem. So that's sort of the basic outline, and stable homotopy theory enters here because it provides a very nice recipe for doing so that I want to advertise. Namely, what do you do? Well, in this particular case, and I guess in general, you pick your favorite tool, namely the atom spectral sequence, which is a hugely powerful spectral sequence that under pretty general conditions computes this mapping space between two spectra in terms of some cohomological data in this sense as modules over the mod 2 Steenrod algebra. So I'll explain a little bit about this in the next couple of slides, but you compute enough about this, at least qualitatively, and then you combine it with Adams filtration bounds on your map. So this is the general outline, and once I've introduced these two concepts, I'll explain why having access to both of these things allows you to conclude that a map is null. Okay, so what is the atom spectral sequence? Very briefly, so take two reasonably nice spectra. Typically you need some finiteness assumptions, and you need a nice spectrum with respect to which you're taking cohomology. Here we'll just be doing everything with respect to mod 2. So this will be the Eilenberg-MacLane spectrum for Mod2 cohomology. And in that case, the atom spectral sequence looks like this. This is the E2 page, and it will converge not quite to the full mapping space of maps between X and Y, but up to some to completion. The to completion corresponds to the prime two that you're taking the cohomology with respect to. But this is not so bad. If you know this factor square, you can sort of figure out information at every prime p, stitch them together with the rational information, and then you can actually recover the full mapping space. So, for instance, if this mapping space here, this is finitely generated in each degree, then this to completion just essentially remembers the two primary part of this finitely generated abelian group. So you're really seeing interesting information, and usually the prime two is sort of the most interesting one. So this is what the atom spectral sequence is. And then another concept that shows up and is of vital importance is the notion of an atoms filtration. This is essentially what you're filtering this mapping spectrum with respect to in order to get the filtration that you then run the spectral sequence machinery for. So if you have a map of a spectra F between X and Y, then we say that it has atoms filtration S or at least S if you can factor it through S of these spaces where each successive map is trivial in an F2 cohomology. So maybe a few remarks just to get you somewhat acquainted with this notion. Every map has atoms filtration bigger than or equal to 0. So that's good. We are seeing every map, and then a map has atoms filtration greater than 1 if it's trivial in Mod2 homology. So atoms filtration in some sense measures how trivial your map is to the point of view of Mod2 cohomology, and then you use that cohomological information to try to build, well, is it then trivial from the point of view of homotopy classes of maps as well? Okay, and the way these two connect together is that the atoms filtration of a map S here will correspond to essentially the y-axis on the E2 page. Okay, so right. So now that we know a little bit about the atom spectral sequence and atoms filtration, let me try to explain to you the general outline of how you combine these two things to prove maps on null homotopic. So let's assume that we're trying to compute the space of maps between X and Y and some to completion like this. And let's say that we somehow know that the atoms E2 page looks like this. So this is going to be sort of a very qualitative rather than quantitative view of the atom spectral sequence. All we know is that there might be stuff here in the shaded area, but outside of the shaded area, everything is 0. The 0 column here is exactly what's going to converge to the space of maps, or like this is what the infinity page is gonna look like. And if I know something about so we can already see here that there's no reason for the whole space of maps to be trivial. But if I'm interested in a particular map and I have some understanding of what its atoms filtration is, even though there might be non-zero elements on the E infinity page corresponding to the shaded area intersecting this red column, if I have a bound, this green dot here, let's say it's D for a specific atoms filtration of an element, well, then I can actually prove that this map is null homotopic because it's going to be somewhere on the E infinity page. It's not going to be in the region where there might be non-zero entries on the E infinity page because the atoms filtration bound pushes it above that line. So it must be in some group that's just simply trivial. So on the E infinity page, I can just exclude it being non-zero, and that means it must be sorry, I can exclude it being non-zero, so that means it must have been null homotopic as a map between X and the to completion of Y. So that is essentially what we'll do. We'll develop enough qualitative information about the Adams E2 page for the mapping spectrum that we're interested in. And then we'll develop Adams filtration bounds and play these guys off each other. And that will prove the theorem essentially. Okay, so as stated, let's get some understanding of these E2 pages. So if you start with, okay, this is annoying, this is on top of my thing. Well, if you start with this standard projective space, move it. No. If you start with this standard projective space, we're going to get some understanding of what the E2 page looks like for this guy. So the cohomology with mod 2 coefficients of this standard projective space is very simple. And one way of drawing it is I'm just going to draw a dot in every degree above 2n, which corresponds to a non-trivial cohomology group. And then the way you depict this usually in this business is that you then interlace the action of the Steenrod operations on these cohomology groups. And for us, we're really only going to be interested in how the first Steenrod square acts. And the way that it acts is it provides an isomorphism between, so maybe I should have drawn some more dots. For an odd guy going to an even guy, this is going to be an isomorphism, so you draw that with a straight line. But for the cell in the bottom degree, it's going to be 0. So even though, of course, this splits as a F2 vector space, the cohomology splits as an F2 vector space, it does not split as a module over the mod 2 Steenrod algebra. So this is just our M, and this is just our F2 in degree 2n. But what is true is that this M is a free module over sort of a smaller subalgebra. Namely, this guy is the subalgebra of the full Steenrod algebra generated by just the first Steenrod square. And this guy is free on that. And that's very useful because sort of early theorems of Adams gives you exactly a vanishing line. So if you look at M and you look at X with respect to F2 as modules over the Steenrod algebra, this has these two ST components. And if you draw how that's going to look in sort of the same Adams diagram, there's going to be a nice vanishing line. So if you look at, if you look at S comma T for this M, F2, and this is going to have a line like this of slope 1/2. So there might be stuff here, but no stuff above it. And this is sort of the starting point that we're gonna use for lots of these computations. And this is not, of course, the full picture for the standard projective space. It's not just M. There's also this F2 guy. But they sit in this short exact sequence. And this short exact sequence of modules over the Steenrod algebra induces a long exact sequence in X. And if you've seen some of these Adams charts, you know that X of this guy is sort of going to be at least a shifted copy of the Adams E2 page for the sphere. And since it's sitting in degree 2n, so let me maybe give this red, this is at least going to contribute a tower corresponding to the pi 0 of the sphere being the integers sitting in degree 0, or here I've shifted it up to degree 2n. So maybe it's believable that if you run the long exact sequence in X, this is going to contribute some cohomology or some entries on the E2 page to the cohomology of the standard projective space as a module over the Steenrod algebra. Okay, so if you run this computation, this is the following result that you'll get for the E2 page of this standard projective space. So this was the tower that I mentioned before, coming from F2. And again, if you've looked at the Adams E2 page for the sphere, outside of the tower that's sitting in degree 0, there is a nice, well, if you make the intercept a little to the left, there's a nice slope of line 1/2. above where everything else vanishes. So that's this slope here. Slope 1/2. And again, I've indicated with dots stuff that might be zero, it might not be zero. The point is we don't really care. We just need this qualitative information about sort of the large structure of the E2 page. Okay, but if you followed along with my general outline, this already seems like a big issue. I've made everything arbitrarily 2n connected by just shifting. So at the end of the day, I'm gonna shift everything down by 2n. And then I can never run this gambit of getting high atoms filtration and playing it off against a vanishing line for my E2 page, because this tower will then live at the 0 column. And no matter how big of an atoms filtration bound I get on a specific element, well, there might always be non-zero atoms filtration elements on the E infinity page that it can land in. So I can't rule it out being 0. So we're gonna have to get rid of this tower somehow. And that's what we're gonna do now. So this tower came about because we had an F2 sitting in degree 2n. So if we kill the bottom cohomology group of this our standard projective space, maybe we have some chance of killing this tower and still retaining a slope half vanishing line. And that's essentially what we're going to do. This e to the s is called the stable cohomotopy Euler class. All you really need to know is that it's a lift of the Euler class. So if you compose further to hz, this becomes literally the Euler class of this bundle. Okay, and if you run through the computations, this is going to tell you that this tower vanishes. And we can, in fact, lift the connecting homomorphism to Y. So it suffices to prove that the connecting homomorphism as a map to Y is null-homotopic, because then the composite is obviously also null-homotopic. And now we can actually implement our strategy. Again, similar considerations as before. You take this exact sequence, you look at it in F2 cohomology, that gives you a long exact sequence, but you actually prove that this long exact sequence becomes a short exact sequence of modules over the Steenrod algebra. Then you run again a long exact sequence in X, and you get this E2 page. So this Y was sitting between, let's just go back, it was sitting between the sphere and RP and the standard projective space, and they each contribute essentially a tower in these degrees. But then in the X long exact sequence, you prove that the connecting homomorphism, which goes, I can't remember, between one of these guys, above a certain degree, is going to be an isomorphism. So you'll have two towers that could potentially interfere, but the way the long exact sequence works, they just annihilate each other. So that's very useful. So this annoying tower that was an obstruction to our plan, we've now gotten rid of. And we have a nice clean slope 1/2 vanishing line with a good intercept. Okay, so that's the control of the atoms E2 page that we need for sort of 1/2 of the recipe. And the second half that we need is bounds on the atoms filtration. Okay, so I'm gonna be throwing a big diagram at you. So bear with me. The way we're gonna get this atoms filtration is the way we constructed the original exact sequence that we're gonna split is compatible with varying the cover, the connective cover that you're taking. So we're actually gonna be able to factor the map that we're trying to show is 0 through this red map, like this. And then we're gonna be going down by commutativity of this diagram here. And these maps, these factorizations will provide the atoms filtration for us. Namely, people have a good understanding of these spaces and these maps. Oh, sorry. not quite. Let me back up. I messed up the order of my slides. All right, so let me recap. This is the map that we're trying to show is 0. What we have access to, or it will turn out what we will access a little better, is this top map here. And there's an obstruction theory argument that I've outlined as a lemma here that tells you that, in fact, precomposing with sort of the skeleton into the truncation induces an injection on homotopic classes of maps. So showing that delta is 0, it suffices to show that this top red arrow is 0. So we want this guy to be equal to 0. That will suffice. And now I can come to the part that I was saying before. So we want this guy to be 0. How are we going to show that it's 0? Well, we're going to gain Adams filtration by going along these maps, because Senger in, I don't know, the 60s or 70s or something, proved that roughly half of these maps are trivial in F2 cohomology, at least up to a point. And we're also going to just restrict by picking a skeleton. So we throw off all the top homology beyond L, so that we can make these maps actually 0 on F2 cohomology, not just in a range. So that's going to give rise to Adams filtration bounds. And in fact, if you do sort of k factorizations, you'll roughly get an Adams filtration of k over 2, because, well, roughly half of these maps are 0. Okay. So here's sort of an annoying thing. The more you gain Adams filtration, the less connective, or the less the range you make, the less you make the range in which you have the exact sequence that you're trying to split. So there is sort of a tension between, well, you want to make L as big as possible, which means you want to get as much Adams filtration as possible, because that will help you show that the map is 0. But gaining Adams filtration means that you're going to lose connectivity of the fiber sequence that you're trying to split. So you're going to have to play a somewhat delicate game of optimizing the choice of how much Adams filtration you gain against how much connectivity do you lose from the fiber sequence. But this is going to be the rough picture. We started out and we said that we computed sort of previously that y had a slope 1/2 vanishing line, and by just essentially again some long exacts manipulations, you can show that if you're mapping in now this skeleton of MON, regardless of what its E2 page looked like, you can actually get a similar slope for this full mapping spectrum, but the intercept is going to decrease by L for every L skeleton, essentially. So that's what's reflected down here, or I guess here. The previous intercept was 2n minus 3, and now it's 2n minus 3 minus L. So the bigger you make the skeleton, which is, again, what you're trying to make as large as possible, you move the whole E2 page to the left, so you'll get more intersections with the 0 column. But again, we're combining it, or this is the tension. If you have Adams filtration D, the point is you want to pick L as big as possible, so you move this all the way to the left, keeping the stuff that intersects the T minus, whatever intersects the T minus S equals 0 column, below this line of Adams filtration D. If you can manage these two feats, then again, by this general recipe, your map has to be null homotopic. So that's an annoying optimization problem, but that's how you get this stuff. So this is just stating what I just said. We want the 0 column to have non-zero stuff only below the Adams filtration bound that we have, and balancing these all out tells you that you have to maximize the integer L satisfying these constraints. So this first guy comes from this annoying bound for these Adams filtration. They're not zero in all of F2 cohomology, but only up to a point. So you want to make your skeleton less than that. This won't really play a role for the optimization. This part is from the connectivity of the fiber sequence. That we're trying to split. And this will be vanishing. How far out do you vanish? This to hn comma k. Hn comma k just counts the number of integers between n and k that are congruent to 0, 1, 2, and 4 mod 8, which are exactly those maps that had that were trivial in F2 cohomology. So this term here exactly counts the Adams filtration of the connecting homomorphism. So if you balance all of this out and you solve an annoying integer optimization problem, then you figure out what k you need to make this L as big as possible. And this is going to give some annoying constant, but roughly the long-term behavior is this 5n over 2. So, and then this constant is like 9 or something like that, close to 9. And essentially it's because there's some annoying stuff in the beginning of, I mean, you can already see it on the E2 page for the sphere. This Hopf invariant business, you have a lot of non-zero stuff already in the beginning. So this slope half, you have to make the intercept very far to the left to get it, to get all the non-zero stuff below that one. And that's why this this constant is rather large. Okay. So that was for p equals 2. There are more primes than just 2, so you should really also do it for the odd primes if you want a theorem that works in general. And the way you do this is that you have this fracture square for any spectrum. You can recover it as the pullback along its rationalization and these p completions. And what you just show is that this guy is contractible and this guy is contractible. So the top map must be an equivalence. So if I want to show that a map into Y is null, I can just show it for each of its p completions. We've already settled the case p equals 2, so we just have to settle the odd primes. And this can just be done directly. So if you again look at this stable cohomotopy Euler class, I claim that this provides a splitting after you p complete at odd primes. And that's essentially because once you p complete everything at odd primes, this becomes, again, a shifted copy of the p completed sphere. And this composite is multiplication by 2, which is a p-adic unit. Oops. P-adic unit. For odd p. So if I want to check a map between two spheres as an equivalence, I can just check it on homology in that degree. And here it's going to be the copy of the p-adic integers, and I'm going to get multiplication by a unit, which is invertible. So you can just split the sequence directly in the range that you have it, which is this 3n plus 1 on p completions for odd primes. So you do get a better splitting if you're just interested in the odd primary information. So the prime 2 is once again the most difficult prime. And putting that all together with the factor square gives you the stated result, namely this sequence is split in the range indicated. Okay. I see I have 10 minutes left. Now you have this computation. Okay, that's great. Can you do anything that's maybe slightly more related to geometry with it? And the answer is somewhat. So again, as I stated in the beginning, the homology or cohomology of these classifying spaces are related to characteristic classes of certain bundles. Now that we have access to the stable homotopy type, at least in a range, there's a nice trick that you can use to actually get at the second homology. It essentially uses that, well, if you have an infinite loop space, this is just a fact that then the first K1 invariant of the Postnikov tower is 0. So the second stage Postnikov truncation is split. And if you manipulate that a little bit, you can actually go from information about the homotopy groups to information about the homology groups. And in this case, you get this determination, which is not super easy to wrap your head around. And we don't currently know exactly, like, this should correspond to some kind of characteristic classes. Can you write them down geometrically? We cannot, which is annoying. But let me convince you that you can somewhat compute this right-hand side, at least in certain cases. So there are these computation groups here and here. They essentially correspond to the homotopy groups of MON. Oops. This one. And then, as I said somewhat previously, there's some algebraic K-theory data appearing here as the automorphisms of the intersection form of middle homology, but this is reasonably well understood. And then there are also some of these stable homotopy groups of these stunted projective spaces, which are also reasonably computable. So I've given you a table here. And then I guess sort of recently we have some access to what these computation groups look like. This for large N means that I want to apply Bourglin, Hahn, Senger. So you can also get lower information, but if you want uniform descriptions, you need N like at least 130 or something like that. And one of these groups is just always the co-kernel of J, so the most difficult part of the homotopy groups of spheres. And this other group is most likely, or at least in half cases, co-kernel of J. And then in the other cases, it might be a non-trivial extension of co-kernel of J. Just to say that, well, if you can compute co-kernel of J, i.e. the homotopy groups of spheres, you can also compute some of these groups here. Okay, and then what are some future applications? Well, okay, what are you actually interested in? Well, you're interested in the homotopy groups of this classifying space. That's going to inform the geometry. And you really only have access to its homology. So you go back and you look at the oldest trick in the book. This is how Sejr, computed homotopy groups of spheres. You kill off enough homotopy groups below the dimension so that you can apply Hurevich and just calculate homology instead. So for H2, this looks like, well, we're going to kill off the pi 1. And that means just taking diffeomorphisms that are in the identity component. And then you get a fiber sequence from this guy going to the mapping class group. You apply classifying spaces to it. And this gives you this vibration here. And now you've made the left-hand term simply connected. So its H2 is also its pi 2. And you can try to then run the Sejr spectral sequence on this. And if you can calculate H2 of this identity component, well, then you win and you can get pi 2. And there are various approaches that look interesting to doing this, but this has not been resolved at all. But using the input that we know H2 of this guy seems useful. And this like, again, the homology and cohomology of this guy is also pretty reasonably well understood. So there is some hope of just running a spectral sequence argument. The only caveat is, okay, this guy is acting on this. So you're probably only gonna get the answer up to some invariance, co-invariance, sorry. And the action is just non-trivial. So you have to see what you can do with that. And then even more hopefully, or even more speculatively, you can actually try to get at some of the homotopy groups of disks, of BDiff, of a disk, which are, of course, sort of the holy grail. And how much work do you have to put in for how much reward? Well, that depends. What the sort of super hope is that if you could calculate pi2 of BDiff of these WG1s, then you can use something called the Wise fiber sequence to relate this to homotopy groups of a disk. And in this range, there is an unresolved set mod 2 coming from this Whitehead spectrum. So in general, you look at this diffeomorphism groups, and then there's a better variant that's called the block diffeomorphism groups. There's a map from one to the other, and the fiber is in a number of degrees approximated by this Whitehead spectrum, or an infinite D-looping thereof, with a C2 action. And on pi2, this guy is just a set mod 2. And so you're going to get a map from set mod 2 to pi2 BDiff of Tn. Again, here you need like n, I don't know, 6 or 7 reasonably large. And it is currently unknown. Well, let's say it's open. Whether this is zero. But hopefully, I mean, yes, I have no concrete, I have a couple of plans of attacks for how this might work out with more information about pi2 of BDiff, but that's sort of that would be a very, very interesting application of these ideas to actually get at some torsion in these diffeomorphism groups. Because right now, what we mainly know is rational information, and that's already very, very hard. And so, just determining some two torsion would be super interesting. Okay, I think that was everything that I had to say. So thanks for listening.
Thank you very much for a great talk.